can start. Andrei Smirnov, lead engineer of Talos, behind all the code. Well, not all the code. Manages all the code. An awful lot of the code.
So I have my talk pre-recorded, but the first few seconds are cut, so I'm going to introduce myself. First, I'm Andrei Smirnov, and I'm going to talk. This talk will be probably going a bit more deep into Talos itself and talking about controllers and resources and how we use them in Talos. So I can answer questions as they come in the chat while the video is playing, and also, of course, after the talk. So let's start. I'm engineering lead at Sidero Labs, and today I'm going to talk about how we built our operating system, Talos Linux, using controller and resource pattern. And instead of using slides, I'm going to share this markdown document today. So what are we going to talk about? First, I'll start with the question, why do we even need to have controllers and resources in the operating system? Then we'll talk a bit more in detail about our own controller runtime that we developed and how it is being used in Talos. And in the end, we'll talk about what's coming next, what might be the next feature of Talos and controllers. So let's talk about the operating systems in general. The traditional operating system, when it boots, it goes through some sequence of actions, which might be called run levels or units, and one unit provides something which is being consumed by other units. So the boot process is something sequential when one thing can be done only when something else was done. Like you have to mount file systems first, then you can start one daemon which provides something to another daemon and so on. And 2 years ago, before we started this adventure into using controllers and resources, Talos worked pretty much same way. It had a sequencer which was running a sequence of actions one after another, and that's how it is. It's very simple. At the same time, the state of the machine running Talos Linux is fully defined by the machine configuration. So if we change the machine configuration, we change the state of the machine. On one hand, you can say that you shouldn't be changing machine configuration too often. But on the other hand, there are many cases when it's pretty much useful. For example, when you're debugging machine configuration or when you are rolling out some changes. For example, you're upgrading Kubernetes in your cluster. If you have a traditional boot sequence, which consists of like steps running one after another, if you want to roll out some changes, the only way you can do that is by rolling back some steps and then rolling them forward once again with the new configuration. But that sometimes or pretty often means that you have to reboot the node to apply a machine configuration change. And that, of course, is not fun, even if you think about a machine which runs on bare metal, when reboot might take tens of minutes. So we come to the idea that the operating system should be reactive, that it should act on changes. And there are many kind of changes or events which might happen in the environment. Some of them are very simple. For example, if someone presses a power button, whether it's like a physical one or a virtual one for in the cloud, the operating system gets a shutdown event and it should do everything to shut down the node. But there are some events which are much more complicated, and they cause many more changes in the machine itself. So let's take as an example a case when a DHCP server hands out a new hostname to the operating system. That's what happens first. We have DHCP server. It sends a new hostname to the operating system. Operating system merges the hostname configuration. For example, if the hostname is overridden in the machine configuration, new hostname from DHCP does nothing, so we have nothing changing. But if we're using actually dynamic hostname, then the OS should actually apply the new hostname to the Linux kernel. And as we have the new hostname, probably we need to rebuild a list of certificate SANs, and we're rebuilding it. And there might be that there is a change and there is no change because we already had that name from some other source. If there is a change, we have to reissue all certificates. And once the certificates are reissued with the new hostname, we have to restart all services which do not handle reloading certificates on their own. And at the same time, if as we're running Kubernetes, the hostname might be used to figure out the Kubernetes node name. And if the node name changes, we need to go back and to update the node name, which means we have to rebootstrap the kubelet because kubelet certificate is bound, client certificate is bound to the node name. So that seems like a pretty complicated sequence of actions happening inside the system, and we can notice several interesting things. First thing is that this change propagation might stop at any stage because there might be no actual change. But on the other hand, there are many pieces of this flow, as I described as an example, which are useful in many other cases. For example, if the node gets a new IP address, we need to update the certificates pretty much same way, or if we have to update certificates because they're going to expire, or just rolling new certificates, we still have to restart the services. So if you think about that, we need to somehow implement this change propagation in the operating system. And it makes a lot of sense to have some kind of events. We can think that we have many, many different components. So probably we're going to have some kind of event bus, and probably these events will carry some data with it. And if we think about all of that, it seems to be really similar to what are the controllers and the resources. And can we use that pattern instead of trying to invent something else? So, first of all, what is a controller? That's a simple loop that watches some input resources. It does some actually, and then it updates the output resources. That's all what a controller is. And the resource itself is really simple. It has some fixed metadata, which is common for all resources. And metadata tells us what kind of resource that is. It tells its ID or name, namespace, labels, and stuff like that, while the resource spec contains the actual data, and the spec depends on the resource type. So if controllers are only watching input resources and modifying output resources, they're not doing any meaningful work. So usually the control loop has some side effects, the actual work that controller is doing. The controller might be interacting with the external services. It might be, for example, doing some syscalls, interacting with the Linux kernel, and so on. There might be some special cases of controllers, for example, controllers which have no input resources. Instead of watching resources, they might be watching some external system, for example, watching Kubernetes API or watching Linux kernel. And same way, there might be no output resources if the controller is the only work of the controller is interacting with some other components. That might happen as well. So once we realize that we want to try to make sure that the operating system is based on the resources and controllers, the first thought that comes to mind is to use Kubernetes, and specifically Kubernetes API server, so we don't have to re-implement things. We looked into that, but at the same time, we had some constraints. We know that the controllers and resources have to run from the very moment that the operating system is booted up, which means they should run when nothing is like mounted. There is no file system. We only have memory. And we want to make sure that the operating system is minimal because Talos Linux itself is minimal and we don't want to bring anything big into that. For some time, we were looking into a KCP project, which was a idea to strip down Kubernetes API server, and to make it more minimal. But that wasn't ready at the moment we started our development, and right now it seems to be going in a different direction. So we thought, what if we implement our own resource model and our own controller runtime? And if we do that, we can try to fix some things which we don't like in Kubernetes as well. For example, the first thing we thought about was a resource ownership. What I mean is not that there is an owner reference in the resource, but rather there is a strict uh, contract that there is a single owner of the resource, a single controller which can modify that resource, and no other controller can make modifications. That came to us as we were doing lots of cluster API development. And when you're trying to debug something or trying to figure out what's going on in cluster API, sometimes it's very hard because you know, okay, this controller is waiting for this resource to be updated, but what updates that resource? No, it's not that controller, it's another controller. And probably there is like the third one, which sets an annotation somewhere. So following that control flow is very hard. And part of the problem is certainly that you have no idea who owns that or who will actually make a modification because many controllers can do that. And also, as we do this strict ownership, we can define a contract for the controller itself to say that a controller has a set of inputs, specific resources it's watching, and outputs. And we also validate against these contracts so controller can't touch anything outside of its inputs and outputs. And also, as I said in the beginning, as we need to make sure that this implementation is minimal, we started with a very simple resource API implementation, which is completely in memory, very lightweight, and uses like minimal uh, copying so that it doesn't copy resources too often and doesn't do any marshaling and marshaling. That was our first goal. Um, but let's take a step back before talking about the implementation, and let's talk about how resources are actually useful, not only as a way to implement something, but also for the users. As the resources connect controllers together, so if we look at each controller, there is some resource which is the input, some other resource which is the output, and so on. So there is like a chain of controllers connected with the resources. By looking at the resources, we can figure out what is going on, what this controller is doing, or why this controller is stuck, why is it's not moving. So we can kind of look into the internals when we need to understand what's going on. Sometimes these resources might be useful for the end user, sometimes they're only useful as a debugging tool, but still having this uniform interface, uniform API to see into the operating system internals is very important. I have some examples here. For example, we have a member resource in Talos, which lists or cluster members. This is like a compact view, and we also have a detailed view which we can get any resource in YAML, JSON. We can apply JSON path. We can do whatever transformation with that resource to gather the data we need. The second thing, if we move from the resources to the next level, are the controller loops. So each controller runs like a loop forever. When it gets triggered, whenever the input resources are changed, then it does some work, modifies output resources, and sleeps once again until the next change comes. Each controller loop runs in its own thread of execution. Technically, for Talos, as it's implemented in Go, it means that each controller runs in its own Go routine, which means that on the other hand, the controllers can run in parallel when they have no dependencies between them. So the Talos can boot as fast as it's possible, whatever is not limited by the dependencies between the controllers, and it can also roll out changes as fast as possible, same way, because all controllers run in parallel. And controller loops are also independent in the sense that if one controller crashes, it doesn't crash other controllers, and the runtime will restart any controller which crashed or simply returned an error. And this restart will be done with the automatic backoff. So that's a powerful tool to handle all kind of transient errors when something needs to be retried. And another important topic is how controllers can help to test the operating system. Testing operating system is really hard because you have to test it in so many different ways, in so many different environments. You can run it with IPv4, IPv6 only, and like dual stack environment. So many different ways to configure things. And of course, integration tests are it's like the best tool to test anything. But sometimes when we talk about edge cases or some specific um, scenarios, we can use unit tests when we test a single controller in isolation. As each controller has a contract, we can always build some inputs, provide some input resources, run the controller, and do an assertion on the outputs to figure out what's going on. We can repeat this and build a set of smaller scale tests for each controller. And that's what we are doing in Talos as well. That, for example, allows to speed up development when we have like just a single controller and we don't have the full flow implemented. We can still do unit tests to verify that controller works as expected. A few words about the controller runtime that we implemented for Talos. We call it Cozy, and probably we're going to rename that. We call it Common Operating System Interface. And Cozy consists of two principal layers. One layer is the resource storage, and another layer is the controller runtime. Resource storage is very similar to Kubernetes in the sense that we have same operations on resources. We can get them, we can modify them. The very first resource implementation is using in-memory storage that's being used in Talos. We can offer like optional persistence to disk. Another resource storage implementation is using etcd. So in that case, multiple processes can see the same state of resources, pretty much like Kubernetes API. Talos Linux is using at the moment only in-memory storage, but This might change in the future. There might be some resources which are cluster-wide and stored in etcd. And resource API is available both in process with minimal overhead, and also it can be accessed over gRPC API. So components running on different processes can get, or different even machines over the network can get access to the resources. And the examples I was showing before with Talos ETL get members is using exactly resource API to get some resources from Talos. And the second layer of Cozy is the controller runtime. It's a system which builds on top of the resource API to provide a framework to run controller loops, to restart them, handle crashes, handle controller contracts, verify inputs, outputs, and so on. And just to give you an example of a controller, I have an example of a controller from Talos. That is a network status controller. It's a very simple controller, which has several inputs. It aggregates the information about the network subsystem state, like it looks into the addresses, routes, hostname, and files under etc, and outputs a single resource, which provides a like bird's eye view on what's going on with the network. Is it ready or not? And this controller, like all others, runs like this forever loop, which it gets triggered by the controller runtime whenever some of the inputs changes, fetches the resources, the dependencies, and analyzes them to figure out whether some condition is met or not. For example, is there a route which is a default gateway? If there is, we assume that network connectivity is ready, and so on. And in the end, this controller outputs a network status resource, which is being used by many other components in the system to quickly see, is the network ready? Can we proceed with some operations? Cozy and in general, the controller resource pattern appeared in Talos 090, which is funny enough, almost 2 years ago. And the very first implementation of the controllers was the Kubernetes subsystem. And that it was the time when Talos transitioned away from self-hosted Kubernetes to running Kubernetes control plane components as static pods. That was kind of an experiment for us. We were looking, okay, is it going to be good or bad if we try to use controllers? That turned out to be really good. And since that time, many more subsystems in Talos were converted to use controllers and resources. And at the moment, Talos has 88 different resource types, not resource instances, but different types of resources. One more important thing which helps with the development is as Cozy enforces a contract on each controller on inputs and outputs, we can also automatically analyze and visualize the dependencies between the controllers. For example, in Talos 09, this is the dependency tree between the controllers. We can see here the, like in light cyan are the resource types and the white ones are the controllers. And the lines connect them together as the flow of data, basically, what is the input, what is the output. We can see that on the top of this graph, yeah, it's a graph certainly, we have the machine configure resource, which contains Talos machine configuration, which makes this graph was created automatically, of course, right? It wasn't done manually, but it shows that everything in Talos is defined by the machine configuration. And we have controllers which are cascading from the machine config down. You can see that most of the controllers are related to Kubernetes, and they're managing the Bootstrap manifests, uh, Kubernetes control plane components running as static pods, and so on and so forth. If we look at the same graph, but at the current version of Talos, that looks like so big that it's hard to see it on a single screen, but it still follows the same property. We can see that machine configuration resource is at the very top, and from that we have many more controllers going down. For example, we can look at some part of this diagram. We have a mount status resource, which describes or reflects the state of the file system mounts, and Talos has a state partition, which contains information about the node. And whenever this partition gets mounted, the node identity controller will either load the node identity from the state partition if it's already there, or if it's a fresh install, it will generate a new random identity and store it there. But once we have the node identity, the identity controller will transform it into multiple representations. One will be machine ID, and another one will be used in the cluster discovery when we have a local affiliate controller which aggregates information from multiple sources about the node. What are the addresses? What is the Talos version, this node identity, and generates an affiliate resource for this node, which will be pushed to the cluster discovery service, and affiliates from other nodes in the cluster will be pulled from the uh, cluster discovery service same way. Then information will be merged, and in the end, the member controller will once again slice the information about the cluster affiliates into the final information about the members, and produces the member resource, the one I had in my example. Uh, Looking at this dependency tree, we can find some patterns which are being used in Talos. For example, one type of the controllers is the controller which watches the Talos machine configuration, which is a big YAML document which completely defines the how this machine should be running. And this type of controllers transform this huge document into smaller sub documents for a specific Talos subsystem. And we do that for two reasons. One is that this way we decouple the subsystem, for example, network subsystem, from the specific Talos Linux machine configuration, which allows this set of controllers to be used outside of Talos, or if we change the machine configuration and format in Talos, the controllers will still stay same because they consume specific to that subsystem configuration. And also another important thing is that these kind of controllers, they stop change propagation. If the machine configuration changes, but it doesn't change anything in the network part, that means that controllers in the network subsystem don't need to be triggered. They don't even need to run. Then we have a set of controllers which are watching external sources. So they're not only watching some input resources, but some external sources. And as an example, I can show the address status controller, which watches the Linux kernel. So, for example, it's using the RT-NetLink API to create a socket into the Linux network subsystem, and we'll get a notification whenever something changes, like a new address is assigned or a new network link appears. And what this controller does, it runs in a loop. Whenever it figures out there is a change to network subsystem, it will pull or get information from the kernel about the addresses, and finally output this information as a set of resources, which can be used to see what are the addresses on the node, and they can be aggregated in different ways. We can, in some views, we don't need information about like link local resources. In other ways, we need them, and so on and so forth. So that's an example of a controller which is using uh, external sources, and in the end it goes like and cleans up the resources it doesn't see in the kernel anymore. For example, if some link disappeared or address was removed. There are controllers which are doing pure resource transformation. They don't have any side effects. Controllers, for example, which manages kubelet, controller which manages kubelet configuration, it gets information from multiple sources. The uh, prepared kubelet configuration, then we have the node name, node IP resource, which provide information about what should be given to the kubelet, and it produces the final kubelet specification resource, which fully defines how kubelet should run. And if that kubelet specification changes, it means that we have to restart the kubelet because something changed. So we get the input resources, we do some transformation, we calculate the args, the kubelet configuration, and so on under some rules. And in the end, we output a resource which fully defines how kubelet should run, including the kubelet, like image, mounts, arguments, configuration, and the node name. And the final type of controllers are the controllers which the most important thing are the side effects. So what these controllers are actually doing. And we can once again look into the kubelet related example. A controller which manages the kubelet, it has some specific phases. We're not going to look into that, but once this controller is running, it watches this kubelet spec resource, the one which was in the previous example, but now it's an input. And also it watches the kubelet secrets, which are needed like to provide the to get the kubelet certificates. And whenever these resources change, this controller writes down the information to disk so the kubelet can pick it up. And then it manages the kubelet service. And service is a component which just simply runs the kubelet as a container in Talos. And it makes sure that whenever we have a change, we stop the kubelet, we restart it, and if needed, we refresh the kubelet certs if there is a change to the node name, and so on. What can we do with Cozy as users of Talos Linux? As Cozy provides an API, we can consume that API and kind of enhance Talos. For example, like if we want to look into resources in Talos, nothing can be more simple than doing that. And I have a very short example here. It's using written in Go. It's using Talos client SDK. So we can build a Talos client which will load configuration from standard Talos config file. And then if we want to get a list of all addresses on the node, we just issue list request to the Cozy subsystem and the client, and then we iterate over the list and print the information from each resource. and we'll get an output like that. So we can see all addresses running on the node. Same way we can watch them, we can get a specific address or any other resource. Here is an example which does a single resource type, but there are 87 other resources which can be queried pretty much same way. Another example is the Talos Cloud Controller Manager, which is a project to help managing hybrid Kubernetes clusters running on top of Talos. And it's built using two features of Talos. One is that whenever Talos runs in the cloud, it extracts the information from the cloud metadata service into the platform metadata resource, which I have an example here, which provides very basic information like the actual platform, region, zone, instance type, instance ID. So each Talos node will present information about the cloud metadata in a uniform way. And another Talos feature called Talos API access from Kubernetes allows to provide access to Talos API from any Kubernetes workload. So we can deploy our Cloud Controller Manager to a Kubernetes cluster running on Talos Linux. And this Cloud Controller Manager will get access to Talos API. It can go to each Talos node, get information about the platform metadata, figure out where each node is running, which cloud it is, and then do the actions that a cloud controller manager should do, but specific to each node, whether one node runs on AWS, another runs on GCP, and the third one runs on Azure, for example. That is pretty much everything I had to talk about Cozy today. And just the last part is what might be coming next. The first thing and the idea we had for a long time as we were developing more and more cozy controllers, it becomes obvious that these controllers are not really specific to Talos, or not all of them are specific to Talos, and that can be useful on their own. And there are many examples like the networking subsystem or time sync or the controllers which actually run Kubernetes. And these controllers can be extracted as separate libraries and they could live on their own, could like evolve, have their own versions. We can even build tests for them. And as these controllers are defined or their API layer are the resources. So for example, network subsystem, what is the input API? The resources which configure the network, the desired configuration. What is the output resource? That's the state of the network. What are the addresses on the node or routes or whether the network is ready? And if the API is fixed, the actual implementation, the controller code could be freely changed. We can drop one implementation and replace it with another. That might be a very powerful idea to have a set of building blocks, these controller libraries, which can be combined together, or we can have some add-ons or plugins to build an operating system the way we want from like different versions of these components. Another idea is around like resource storage. Right now, Talos, like I said, stores all resources in memory. So it means that whenever the node is rebooted, all the resource state is lost. But some resources, it doesn't make sense that they're specific to the node. Like there are cluster-wide resources. And it might be nice to store these resources in etcd. And Cozy provides a way to do that because in Cozy, each namespace can be backed by its own resource storage. So we can have some resources in memory, local to the node, some resources being cluster-wide, which describe cluster state. And also, one thing we would like to look into next is to have a way to extend Talos by providing more cozy controllers and resources. What if we can run a cozy controller in the cluster itself, or outside of the cluster, or running on the node but not being part of a Talos itself? And then these controllers can provide their own resources, or they can plug in into existing resources. They can change the way the node boots. We can imagine an extension to the network subsystem like a BGP extension, which does additional BGP configuration like virtual IP and interacts with the network subsystem, and configuration subsystem, and so on and so on. Or we can think about changing the like probably not changing, but running like some kind of a security controller completely outside of the cluster, uh, which watches the node's state and can like taint a node if there is some kind of a security issue that this controller might notice. There are like probably many or endless ideas about the way this can be extended. And as the cozy provides the runtime and resources provide an API, we can have like multiple implementation which have a common contract that they agree on. So this extensibility becomes really possible. And I think that might be a really powerful concept. That's all I have today. So thanks for watching, and I'm ready to answer any questions you might have. So I'm back live, and thanks for watching. And we have some time. I believe we have a break, so I can answer any questions you might have. I shared the link to the Markdown document. It has links to the code examples and more examples than I had time to show in the talk itself. But I think it's the first time we're publicly talking about cozy. Andrew is asking a question. Do you think we will use the internal resource specs for multi-doc config? I think that's an awesome question, and I'm going back and forth about it myself. On one hand, it's nice to have a single configuration spec that can be shared like both externally and internally in the resources, but so it saves time, development time certainly. But on the other hand, like the configuration is an external contract of the system, and it might need to have a different compatibility guarantees versus the resource spec, which might evolve much more quickly or have like less compatibility guarantees. That it will be tough, but certainly we should think about this more. There is a question in a message bus subscription system to notify about updates to inputs, or all controllers constantly pull cozy. So I think it's a question about this pops up. So cozy is built on top of resource API, and resource API has a very efficient watch implementation. So what controller runtime is doing, actually, it's setting up watches for all controller inputs for all controllers which are running at the moment. And so it's watching a resource or a resource group like single time for any number of controllers which have that as an input. And whenever that resource changes, it will trigger all controllers which are subscribed to it, which have that as an input to run. So in that sense, there is no polling. It's very efficient, and it works same way with like in-memory or etcd implementation. So it's trying to minimize the load on the resource API. And another question from Alexander: is observability a challenge with these controller loops type of systems, since it's pretty hard to have tracing and understand what triggered the initial event? That's a good question. From my point of view, like the practical experience, debugging Talos, something which is written in controllers and resources is usually easier to debug, because having a way to watch even in real time using Talos CTL what's going on with the resource is way easier than going over any other kind of like sequential code. And what if you want to debug that, the only way you can do that is by adding like more logging, more prints to the code. So you have to like repeat the debugging cycle. You look into something, you have no idea what's going on, then you have to go back, add more logs, restart it, watch it once again. With resources, in some ways, you have these debug logs everywhere already, and you have a uniform way to access them. So that sounds for me even better. And another aspect I already touched on is the way you can build tests for resources. So for controllers, I'm sorry, not for resources. So for example, if I have a regression somewhere, so someone found a bug in Talos, and it's something which will be hard to do an integration test for. Instead, I can easily do a unit test first while the bug is there, verify that the test fails, then fix the bug, and I can leave this unit test, and that unit test will run in milliseconds and can verify something. There is a question from Eric: what about security? When injecting Talos credentials into a pod controller, could we restrict which resources the controller can access? So I think that's the question about Talos API access from Kubernetes. So that is, first of all, it's not enabled by default, so it's like a completely opt-in thing. It can be restricted in multiple ways. You can restrict which Kubernetes namespaces are allowed to use this feature. That's the, I think, the most basic form of restriction. Like you can say only like kubesystem namespace can do that. And after that, you can restrict the Talos API roles that the actual pod gets. For example, you can limit to the OS reader role, that's a Talos API RBAC, so to make sure that this specific workload will only see, not only it won't be able to make any changes, but it won't see any secrets, because by default, reader role is restricted to whatever doesn't contain any secrets, so it can't elevate privileges. But at the same time, it allows to like build these extensions. It doesn't have to be only cozy. For example, we have a simple extension which provides a etcd backup. There is a special Talos API role, and the only API it allows is to take a snapshot of etcd database. And so you can build an extension which runs like in cluster and takes a periodic snapshot of etcd, the Kubernetes one, and uploads that to, I don't know, AWS S3, for example. So I think it's the time for the, no, we still have 5 minutes, so I can take more questions.
Yeah, there's time for more questions. Yeah, your scheduled time is finished, but you do have another 5 minutes. If there is any further questions. Or maybe we get to go to the bathroom. So coming up at 10 minutes past the hour, we actually have our first two track going on, two sessions simultaneously. One is from ZenLayer, another cloud provider, about how they orchestrated bare metal Kubernetes cluster creation. It's quite technical. And then there's a kind of a user story that's going to be less technical about how Talos helps save video games. So those should both be interesting in about 4 minutes from now. And if there's anyone that has any last minute questions for Andre, then he's still here.
And of course, yeah, I can take questions on Slack. Always email, GitHub issues.
All right. Well, thanks, Andre. And we'll see you all in one of the two sessions next.
Thank you.